Okay, so here's a quick video to take you through one of the kind of tough questions here when it comes to determining empirical formulas and then a actual molecular formula for a unknown compound. So we've got this compound, and it's made up of three elements. So it's got carbon, it's got hydrogen, and it's got oxygen. And we don't know what the empirical formula is, but what we did do was we burnt it. So we burnt it with lots of oxygen, and we got out of it carbon dioxide gas, and we've got some water. Now, the carbon comes from that carbon, and the hydrogen comes from that hydrogen there. The oxygen is going to be a mixture. It's going to come from both the air and the compound. So our first step here is to determine the amounts of carbon and hydrogen. Now that might seem a little tricky. We have to remember that this initial compound had a mass, and that mass was equal to 1.46 grams. Now when we went and burnt the compound, we got some masses of carbon, and we got 2.79 grams of carbon dioxide, and we've got 1.71 grams of water. And one of the things we need to remember is that if we know a compound, we can use the percent composition of an element in a compound to determine how much of that element in terms of mass is actually in that compound. So if we do percent composition of carbon in CO2, we determine that by taking the mass of carbon, which is 12 grams per mole, and dividing it by the molar mass of carbon dioxide, which is 44 grams per mole. And what I'm not going to do is bother multiplying it by 100, because if I do that, then I have to go and divide out by 100 again. So 12 divided by 44 is 27.3%. So I get 0.273, and I'm rounding here to third decimal place. All right, so now this is useful because now I can determine the mass of carbon. So this was the mass of CO2. The mass of carbon is going to be equal to the mass of CO2 times 0.273, because that's the percentage of carbon in carbon dioxide. And so 2.79 times 0.273, and we're going to get 0.762 grams. Now I've gone 3 decimal places here. That's actually one too many because we only measured at 2 decimal places, so 0.76 grams. Now I'm going to do the same thing for hydrogen. So percent hydrogen in H2O. Now we've got 2 hydrogen atoms in there, so each of them would have a molar mass of 1, so that's going to be 2 grams per mole. All right, that's what the hydrogen is going to make up. And the molar mass of water is 2 plus 16, so that's going to give us 18 grams per mole. Remember that oxygen's molar mass is 16. And so let's figure this out here. 2 divided by 18 equals 0.111. All right. And so now I can find the mass of hydrogen if I take the mass of H2O and I multiply it by 0.111. So 1.71 times 0.111, and I'm going to get 0.1898, so it's going to round up to 0.19 grams. So now I know the amount of carbon and hydrogen in the original formula. So once I have that, I can determine the amount of oxygen in there. So that's my second step. All right, and I know that my total sample, the mass of CXHY OZ, is going to be equal to 1.46 grams. And that's going to be equal to the mass of carbon plus the mass of hydrogen plus the mass of oxygen. And I know the mass of carbon and hydrogen, and I don't know the mass of oxygen. So the mass of oxygen is going to be equal to 1.46 minus the mass of carbon plus the mass of hydrogen put together. So 1.46 minus 0.76 plus 0.19. All right, let's see what we get. And we get 0.51. So now we know the masses of all of our elements. So once we know mass, we can solve for moles. So step 3, solve for moles, and then molar ratios. All right, so we're going to go moles of carbon is going to be equal to 0.76 grams divided by 12 grams per mole. Moles of hydrogen is going to be equal to 0.19 grams divided by 1.0 grams per mole. And then the moles of oxygen is going to be equal to 0.51 grams divided by 16 grams per mole. All right, now this becomes really straightforward. So 0.51 divided by 16, I had that teed up on my calculator, so I'm going to do that one first. 0.032 moles. Kind of did some rounding there. 0.19 divided by 1, of course, is going to be 0.19. And then 0.76 divided by 12 is 0.063. All right, so now to find our ratio, we're going to divide by the smallest number, which is 0.032. All right, and from here we're going to get a ratio of carbon to hydrogen to oxygen. And so 0.63 divided by 0.32, that's going to be pretty close to 2. Yeah, 1.968, so we're going to make that a 2. And then a 0.19 divided by 0.032. See what we get there, 5.9, so that's going to be a 6. And of course, this is a 1. So our empirical formula, I'm just going to write it, take this and put it over here. Therefore, the empirical formula is C2H6O. So now, this is part A done. Woohoo! All right, now for part B. Part B is really straightforward. For part B, we know that the actual molecular mass is 92.16 grams of the real compound. And with organic compounds, a lot of organic compounds have the same empirical formula, but in the end, the actual molecules can be big or small. And so we need to see if this is the actual molecule. So what we're going to do is we're going to find the empirical formula molar mass. All right, and then we're going to compare it to the actual molar mass. So we've got 12 grams per mole for the carbon times 2 plus 1 gram per mole times 6 for the hydrogen, and then 16 grams per mole times 1 for the oxygen. So 24 plus 6 plus 16, and that's going to give us 46. Now right away we can see when we compare 46 to 92, 92 divided by 46 is going to be equal to 2. So this little comparison here is super important, because what that tells us is that our empirical formula is only half of what it should be. So we need twice as much of each atom. So therefore, the molecular formula is, and we're going to multiply everything by 2. So C2 becomes C4, H6 becomes H12, and O1 becomes O2. There we go. And that's the molecular formula. A and B all done there. All right, gang. So again, when we go to do a question like this, the first thing we do is plot our course. What do we know? We know the initial mass of our substance. We burnt it with oxygen. We produced carbon dioxide and water. And we know the masses of each of those. If you know the mass of something, and you know its chemical formula, you can figure out the mass of each element within that compound. All right? And you use percent composition to do that. Percent composition. Who knew how useful it would be? All right, I did. I'm a smart guy. All right, so once we are able to determine the masses of our elements, we can solve for moles. Once you know mass, you can find moles. Once you have moles, you can find molar ratios. And then empirical formulas just fall into place really nicely. So I hope this is really helpful for you. You might see a question like this on a test sometime or an exam. Good luck.